And let's first look at what do we mean by the separable hyperplane theorem. So it says that if there are two non-empty disjoint convex sets, so we're saying we have two non-empty disjoint convex sets, then there exists a hyperplane separating them. Hyperplane separating them such that one set lies on one side of the hyperplane and the other set lies on the other side of the hyperplane. In 2D, this hyperplane will be a straight line in 2 dimension. And in 3D, this hyperplane is a 2D plane. So this is what the separable hyperplane theorem is. Now we want to look at examples to show how each condition is important. The condition was that they have to be non-empty, disjoint, convex, the one we highlighted. How each condition of separable hyperplane theorem is important. And recall the conditions were that we highlighted that they have to be non-empty, disjoint, convex. Let's first look at non-empty. The two sets have to be non-empty. That was the first condition we highlighted because the hyperplane, which in the case of 2D is a straight line, in the case of 3D is a 2D plane, because the hyperplane separates the elements of the two sets. So if there are no elements, it can't separate them. It can't separate them. So the condition of non-empty is important. And disjoint is also required. The second condition that we highlight was they have to be disjoint. By disjoint, we mean that the intersection has to be the null set. For the two sets, so two sets are disjointed, the intersection is the null set. Now let's look at a counter example to show why this is important. So let's look at an example in 2D. So looking at an example in 2D, we have these two sets. One is this set A, right? And we have another set B. So looking at this example in 2D, where we have two sets, right? So they're not disjoint, right? So they're not disjoint because to be disjoint, A intersection B should be the null set. So we have two non-empty convex sets, but they're not disjoint. So we can see we cannot find a hyperplane, in this case a straight line, to separate them such that one will lie entirely on one side and the other set will lie entirely on the other side of the hyperplane. So this example proves we do need disjoint. Because in this case, even though they're non-empty, they are convex, but because they're not disjoint, A intersection B is not equal to the null set, you cannot find a hyperplane, in this case a straight line, to separate the two sets such that, one like this lies on one side and the other lies on the other side. You can't find a hyperplane like this, so disjoint is required. Now let's look at to show convex is also required. Now let's recall what do we mean by convex set first. A convex set is one where you can take any two elements inside the set and join them with a straight line, and that straight line will also lie inside the set. So to show that convex is required, again, let's look at this example in 2D. We have these two sets in 2D. This is set A and this is set B. Now, A is not convex. Now, A is not convex, and let me just make B here. Now A is not convex, right? Because here you can take two elements inside the set, like this element and this, and you join them in the straight line. That straight line does not entirely lie inside the set. We can see we have this example in 2D where we have two non-empty sets that are disjoint. The intersection is the null set. But because one of the sets is not convex, we cannot form a hyperplane, in this case a straight line, such that one lies entirely inside it and the other lies on the other side of it. So we've shown this counter example, the convex is required, by showing that there is a case where you have two non-empty disjoint sets, but one set is not convex, the other is convex, and in this case, you do not have a hyperplane separating them. So this shows that convexity is required. You can, for this condition to always hold. Now let's look at how do we mathematically formulate it. How do we mathematically formulate the separable hyperplane theorem? We right now looked at it in words. So we're saying, okay, let A be two sets as a subset of Rn, be two non-empty convex disjoint sets. So we're saying again the conditions are non-empty convex disjoint sets, and we looked at examples to show how they need to be non-empty, how convexity is important, because if one of the sets turns out to be not convex, then it's possible that we may not be able to find a hyperplane separating them. So it is important for them to be convex, and they have to be disjoint, because if they're not disjoint, then you may not be able to find a hyperplane separating them. And that's then there exists P that belongs to Rn such that, now here a very important term is going to come, such that P is not equal to 0, and C that belongs to R such that, so this is how you can mathematically formulate it. P dot X is less than equal to C is less than equal to P dot Y. So all X that belong to A and Y, then this is how you can mathematically formulate the separable hyperplane theorem. Again, the two sets need to be non-empty, convex, and disjoint. If that is true, then it says there exists a P that belongs to Rn such that P is not equal to 0. It's important it's a non-zero P, and C belongs to R such that we have this two. And here this we're talking about is a dot product between P and X. P dot X is a dot product of the vector P and X. And here this is also the dot product. Now let's look at what if we omit the P not equal to 0 condition. Now P not equal to 0 is a very important condition, as the separable hyperplane theorem, SHT, talks about non-zero vector P, right? It's a very important condition. If we remove P not equal to 0 in the separable hyperplane theorem and you formulate it mathematically, then this is not the separable hyperplane theorem. And this is true regardless of whatever A and B are. So in that case, this is not, and it will be true regardless of whatever A and B are, right? Then in that case, if we just remove the fact that P is not equal to 0, then this is not the separable hyperplane theorem, and this is always going to be true regardless of whatever A and B are, right? We don't need them to be disjoint, non-empty, convex. That statement is going to be true anyways. Why? Because we can take P to be equal to 0. Because remember, we have to just show, what does this mathematically show? Let A and B be subsets of Rn, be two non-empty convex disjoint sets, then there exists a P. So we need to find the existence of this P vector to prove this theorem, right? So if we remove the condition that P is not equal to 0, then this is always true regardless of whatever A and B are, because you can always find a P which is 0, because again it says there exists. And when you want to prove an existence theorem, we just need to prove that there's that exists one such thing, right? So here we've shown, okay, there exists a P, so we can take, so there exists a P which is 0, that belongs to Rn, and there is a C which is equal to 0, that belongs to R. Then, P dot X is always going to be 0 for all X that belong to A, right? Whenever you're taking a 0 vector and you're taking dot product with a 0 vector, you're going to get a 0 regardless, right? Similarly, P dot Y is also going to be 0 for all y that belong to B. So in that case, it will turn out that P dot x, which is 0, is less than equal to C, which is 0, is less than equal to P dot y, which is 0. This was P dot x in that, this was C, and this was P dot y. So when you mathematically formulate it, it's very important that the P vector is non-zero, because if we remove this condition, then this statement is not the separable hyperplane theorem. It is true regardless of whatever A and B are. It doesn't matter whether A are disjoint, convex, or non-empty. And this is not even the separable hyperplane theorem, right? It's going to be true regardless of whatever A and B are, because you just need to find there exists a P and C, right? And we can find that P to be the zero vector because we've omitted the condition P is not equal to zero, and we can take C to be the zero real number. Then in that case, then this will always be true because P dot x is zero, P dot y is zero, and C is also zero. So the condition P dot x is less than equal to C is less than equal to P dot y is satisfied regardless of whatever A and B are. So that's why when you're mathematically formulating the separable hyperplane theorem, that P vector that exists has to be non-zero, right? So it says, okay, let A and B be two non-empty convex disjoint sets, then there exists a P such that the P is not equal to 0 and C belongs to R such that P dot x is less than equal to C less than equal to P dot y.